Muito boa tarde. É com um enorme gosto que temos aqui hoje conosco o astronauta Jeff Hoffman. I will now switch to English. So, hello, we welcome astronaut Jeff Hoffman. Astronaut once is astronaut for life. In this, we'll have the opportunity to hear him about his incredible experience of, namely, you all know, the person who repaired the Hubble Space Telescope. And so it's due to him that we have the wonderful images that have made us dream all these years. This was an opportunity given by Portugal Space, the Portuguese Space Agency. I will just very briefly introduce astronaut Jeffrey Hoffman, and immediately I'll pass to my colleague Hugo Costa, Vice President from the direction of the Portugal Space Agency, to explain better the context why Jeff Hoffman is here with us today. Jeff Hoffman made 5 space flights between 1978 and 1997, becoming the first human to log 1,000 hours of flight time aboard the space shuttle. He also performed 4 spacewalks, including the first unplanned contingency spacewalk in NASA's history in STS-51D. Probably you'll talk about that, in April '85, and the initial repair rescue mission for the Hubble Space Telescope in December 1993 in the STS-61. Jeffrey Hoffman repaired the telescope's primary mirror and helped to replace its 12-meter solar panel. Because of this mission, he became known as the Hubble Repairman. By the way, we have a little piece of the original Hubble panel here. And it was given to us by ESA in the first exhibition that we did when Portugal became part of the European Space Agency. Today, Jeff Hoffman is professor at MIT Aeronautics and Astronautics Department. He's a PhD in astrophysics from Harvard University and an MSc in material science. I find this is interesting for you to see how much have the astronauts to study to be able to be up there and study in different disciplines and in different contexts. So after having a PhD in astronautics, he has an MSc in material science. He was also the astronaut office representative for extravehicular activities, and he helped to develop and carry out tests of advanced high-pressure spacesuit designs and new tools and procedures needed for the assembly of the ISS. So a good topic to ask him questions as well. His primary research now includes precisely improving the technology of spacesuits and designing innovative space systems for human and robotic space exploration. He is also deputy principal investigator of an experiment on NASA's Mars 2020 mission, which will, for the first time, produce oxygen from extraterrestrial material. Of course, a critical step in the future of human space exploration. So we will hear Jeff soon. I now pass to Hugo to explain better the context of his presence in Portugal.
Oh. Muito boa tarde a todos. Good afternoon, everyone. Back in 2008, I did a program called Space Studies Program. And I had the pleasure to be taught by Jeff Hoffman, who was a professor at this program from the International Space University. And also there's a colleague, I see she's here, Sandrine, who also was in the program with me. It's good to see you here as well. And it was amazing all what we learned with Jeff and all the journey he explained us also on, in this talk on how during his astronaut life. Now I'm in the Portuguese Space Agency, and together with Instituto Superior Técnico, we brought the Space Studies program from the International Space University to Portugal, and it's just started last week, and this is the second week of the program that will go until the end of August. And as always, Jeff Hoffman joined the program to teach during the program, and after knowing that Ciência Viva had also here this piece of the solar panel, we thought that would be great to hear the story of this small piece by Jeff Hoffman, who did the exchange of this panel and having first person his experience, and so he can tell us about it. So it's a great honor for us to Ciência Viva, and thank you very much to open your house to receive us and to receive Jeff as well. Thank you very much for being here. It's an honor and a pleasure to have Jeff Hoffman with us and hear again your amazing story. Thank you very much, Jeff.
And now,
Please
Jeff.
join us.
Okay.
Very nice to have you here.
Thank you.
Thank you.
Just one thing I have to correct, Anna, and that's you said our experiment on Mars will produce oxygen. No, it has been producing oxygen since April of 2021. So it's working, and as you say, it will ultimately be important for human exploration of Mars. Let's be sure how this works. Okay. I'm wondering, is the light okay? Everybody can see? Good. Right. Hubble Space Telescope. First thing I want to talk about is why bother to put a telescope in space? I mean, it's a lot less expensive to build a telescope on the ground. But when you're on the ground, you have to look through all of this atmosphere. The atmosphere is constantly moving around, so it blurs the images, and it absorbs a lot of the electromagnetic radiation that we would like to be able to study. So early in the history of the space age, there were some far-sighted astronomers who talked about what could be done if you put a large, optically perfect telescope, and that, when I say optically perfect, I don't want to get too deeply into physics, but for those of you who know about diffraction, it means that you are diffraction limited. In other words, it's the size of the mirror, which means the mirror has to be unbelievably flat with no imperfections. If the mirror were the size of the continent of Europe, the maximum deviation you could have would be about 1 or 2 centimeters from being perfectly flat. So it was a big challenge. And the reason that they wanted to do that was the idea that a telescope like this above the atmosphere could give us an unprecedented clear view of the universe, far, far away, even looking back towards galaxies that were formed near the Big Bang 13.7 billion years ago. So this was the dream behind Hubble, and we built the telescope. The other part of the concept was when we have telescopes on the ground, of course, the fundamental part of a modern telescope is the mirror. Once you've built the mirror, then there are many different detectors that you can put at the focus of the telescope to measure and analyze the light. And those detectors continually improve with time. Now, normally, when you launch a satellite or any sort of a telescope before Hubble, once you launched it, whatever instrumentation you had, that's what you were going to have for the rest of the life of the telescope. Whereas on the ground, when you develop new instruments, you can take out the old ones and put in new and better ones. And of course, if something goes wrong in the telescope, you can fix it. So this was the dream of Hubble, not only to put an optically perfect telescope in space, but to make it serviceable by space-suited astronauts working from the space shuttle. So I look at Hubble as one of the two real legacies of the space shuttle era, the other, of course, being the International Space Station. It was a big challenge. Nobody had built a telescope like this before, and as you can imagine, it was over budget, it was behind schedule. There were a lot of articles criticizing NASA, but in the end, in the spring of 1990, the Hubble Space Telescope was taken into space by the Space Shuttle Discovery, and there was a lot of excitement. Some of you may be old enough to remember this. There were a lot of news articles on television. People were very excited about the incredible view that we would get of the universe. And you have to realize the excitement about Hubble when it was first launched to understand what a disaster it was when, a month or so later, the astronomers, when you pick up a pair of binoculars, the first thing you do is you take the focus wheel and you go back and forth and you find the sweet spot in the middle, and that's what you do with the telescope. But with Hubble, they went back and forth, and this is the best that they could get. I mean, it was a disaster. Again, if you hadn't lived through that, you don't remember, but Hubble was denounced on the halls of the US Congress as a techno-turkey. It was late-night comedians on televisions made jokes about Hubble. Hubble was compared to the Hindenburg and other great disasters of history. It was an absolute disaster for NASA, for the astronomical community. Also, remember, this was the early 90s, and at that time, NASA was trying to get the US Congress to approve money to start work on the International Space Station. Well, NASA was not very popular in Congress, as you can imagine, and the basic response was, hey, do something about Hubble, then talk to us about the space station. So, what do you do when you have a serious problem like this? Well, if you're going to solve the problem, the first thing you want to do is to understand what caused the problem. And I'll give you a brief explanation, and I'll actually give you some details that I found a lot of astronomers don't even know exactly what went wrong. I mean, we knew that the shape of the mirror was fundamentally wrong, but how did it get to be that way? And that's what the next thing I'm going to show you. So here's basically, again, I'm not going to go into too much technical detail, but you need to understand how the telescope works. Light comes in. This is the primary mirror, which has to be incredibly flat, smooth, and the light bounces off that. It then bounces off a secondary mirror, comes through a hole in the center of the mirror, and then you have all of the detecting instruments here, each of which has a little, you can see that little mirror there at 45 degrees. It basically, these instruments all share the light that's coming through, and they deflect a little bit of the light into the instruments. And so that's basically how Hubble works. Now, this is the Hubble telescope. The mirror is actually at about here. This is where the light comes in. It bounces off the secondary mirror, and back here are where all the instruments are located. Now, how do you make a mirror for a large telescope? The Hubble Space Telescope used basically the telescope technology of the mid-20th century. You start with a big piece of flat glass, and then you grind it to make just the right shape. How do you make just the right shape? You need an instrument which will measure the shape as you're grinding it. If you get the wrong, this is how a good mirror should work, where all the light, whether it hits near the center of the mirror or the outside of the mirror, it all comes to a focus at the same place. If you can see if the mirror is a little bit too flat or too curved, then this outer ray is going to end up focused at either too close or too far away, and that's called spherical aberration. That's what you want to avoid, and that's why you need to very precisely measure the shape of the mirror. And the way we do that is you can think of this as a kind of a miniature telescope, which you put near the focus of the mirror, and that allows you to measure the shape of the mirror. It's absolutely critical that you put this measuring instrument at just the right place. And in order to do that, they designed on the top of the mirror, right up here, basically, there was a flat plate with a little hole in the middle. And the idea was you would shine a light that would go through that hole, and it would reflect from the very top of that mirror, and that would allow you to measure very precisely how high the mirror was and get it at just the right place so that it would do the right measurements. The problem was they were worried that some of the light might reflect off this cap itself, and so they put an anti-reflective coating on the entire cap. Now, after the disaster, when they discovered that Hubble couldn't focus properly, of course, there was a team investigating the problem. They went to the factory where the Hubble mirror was made in Connecticut, and they found this cap, which goes on the measuring instrument. And what they found was that a little bit of that anti-reflective coating had come off. And so the result was, this is the way it was supposed to work. The light was going to go through that hole and bounce off the top of the, what we call a measuring rod, and that would be at just the right place. Instead, what actually happened was, when the technician installed this, he actually, after the fact, he said, you know, I had a lot of trouble installing this. I had to put in several little shims of metal to get it at just the right place. That should have been a red flag, and people should have gone in. And there are lots of places in the story where if only somebody had paid a little more attention, maybe we would have discovered this. But what actually happened, you can see the light, instead of reflecting off the top of the measuring rod, reflected off the top of that cap, as a result of which that measuring instrument was put 1.3 millimeters too close to the mirror. And the result was, it said that the mirror was the right shape, but in fact the mirror was slightly too flat. A little bit too much glass had been taken away from the outside of the mirror. How much? About 1 micron, 1/1,000,000th of a meter. The average human hair is about 50 microns. So the error in Hubble that caused this disaster was 1/50th of the diameter of a human hair. But Hubble's optics are so precise that that made all the difference. All right, we know what the problem was. Now what are we going to do about it? And all sorts of things. I mean, you can't take up a new mirror into space and put a new, that's much too big. You can't do it. You need some other way. Lots of studies, astronauts, astronomers, optical engineers, mechanical engineers. Here's what we finally came up with. As I said, this is the way the normal instruments would have functioned, is you have the light coming down, each instrument has a little mirror which intercepts some of the light and reflects it into the instrument. The way that we fixed it was, for each of those instruments, we had to install 2 little mirrors, each of them about the size of your thumbnail, so that the first mirror would intercept the out-of-focus light, reflect it off another mirror which was slightly curved to compensate for the lack of curvature of the primary mirror, and then that light would be reflected into the science instrument. Now, we didn't deal with 24 different mirrors. They were all put into one apparatus, and in fact, this is that apparatus which is now in the Smithsonian Air and Space Museum. You can actually, if you're building a new instrument, you can build this corrective optics, we call it, into the instrument itself. And over the years, because remember, I was on the first servicing mission, but we've serviced Hubble 5 times, and in the end, now all the instruments that are in Hubble have this corrective optics built inside, and so on the final mission they were able to remove what we had installed, and I'll show you pictures of all that process later, and so now it's on view in the Smithsonian. But in any case, so now we knew, well, at least we hoped that we knew how we were going to repair Hubble. In the astronaut office, of course, as you can imagine, this was a primo mission. Who was going to be on the crew to go up and actually do that? NASA wanted to do everything possible to reduce the risk of failure. And so they said, only people who have previously done a spacewalk can be assigned to do the spacewalks to fix Hubble. And as you heard in Anna's introduction, on my very first space flight, we weren't planning to do a spacewalk, but one of the satellites we launched didn't turn on properly, and so we had to make these 2 little tools and go out and attach them to the end of the robotic arm. There was a little switch on the outside of the satellite that we then, the next day, we rendezvoused, and we used that to flick the little switch to turn on the satellite. So I had my spacewalker's union card, so to speak, and was lucky enough then to be assigned, together with 6 other astronauts, 3 of whom would also be doing spacewalks. So all of us had flown before. The commander, Dick Covey, the co-pilot, Ken Bowersox, my EVA partner, Story Musgrave, the other EVA team, because there were not just the optical corrections that had to be done. We had problems with the solar panels. In fact, we removed one of them, and here it is, right here. There were also a lot of the electronics instruments had broken, and so there were actually a dozen different things we had to do, and it was going to take 5 days of spacewalking. And the shuttle could only stay up for about 11 days, so we had to do those spacewalks every day without any rest, and we determined it's better to have 2 teams of spacewalkers. So Story and I would go out on days 1, 3, and 5, and Tom and Kathy would go out on days 2 and 4. So there we are. A lot of training for a critical mission like this. Training for the robotic arm operator, which was Claude Nicollier, who is a Swiss astronaut from the European Space Agency. The European Space Agency actually provided the initial solar arrays and paid for about 15% of the cost of the Hubble telescope, and so it was appropriate to take a European astronaut with us. We introduced for the first time virtual reality into our training. It's now used as a standard tool for getting ready for flights. Of course, for those of us who were going to do spacewalks, it was working underwater where we spent most of our time. We spent about 400 hours underwater training for this mission. And the reason is, a spacesuit here on the ground weighs about 300 pounds. Now, of course, up in space, it doesn't weigh anything. That's, what, 130 kilos, roughly. If I were wearing a spacesuit, I could barely stand up, much less do any useful work. But when you go into the water, the spacesuit is filled with air, so it wants to float up to the surface. And so what they do is then they put lead weights in your chest and your legs and your arms so that you become neutrally buoyant. You don't float, you don't sink. And it's the closest approximation we can come to be able to work with a spacesuit. It's not exactly the same, and some people have gotten confused because when they get up into space, they think that they can do everything they could do in the water. That's one of the reasons why they wanted experienced astronauts who had done spacewalks, so that we knew exactly what we could and could not carry from the water up to space. But we spent a lot of time going through all the procedures which we were going to do, because remember, we only had 5 days to do the work. So the amount of time that we would spend outside was really what was going to limit what we could do. It was what we call a limiting consumable. And we had to work to make sure that we could do everything as efficiently as possible. I mean, the last thing you want to do is to go out and do a job and realize, oh, I don't have the right tool. I've got to now go all the way back to the airlock, get the right tool, come back, and I've just lost 30 minutes, which you just can't afford to do. You'll see this is a model of the wide field camera, which really, this actually had corrective optics built into it when we installed it. And this is what, for about the first 20 years of Hubble, took all those incredible pictures you saw. And then eventually on the last mission, they took this out and put in an even better one. And we spent a lot of time at the Goddard Space Flight Center. They had a clean room where they actually had full-scale models of the Hubble Space Telescope, and they also, that gave us an opportunity to look at the actual instruments that we were going to put in. Obviously, you don't take something like this and put it in the water. So it's nice, after working with the models that we work in the water, to actually see the real instruments that we're going to be using. So we go down now after over a year of very intense training. We get in our little NASA airplanes. We fly down. You can see our shuttle on the launch pad. It's always exciting. Normally, airplanes are not allowed to fly in this area, but whenever the astronauts come down before the flight, they give you special permission, because all the people working at the Kennedy Space Center, they love to see the planes fly around the launch area, and of course we love it too. It's you really feel now something serious is getting ready to happen. And then the night before the launch, we actually had a total eclipse of the moon, which was especially nice. But you know, they light up the shuttle and we all go and you stand at the bottom and you look up at this incredible thing that's going to take us up into space the next day, and there it is. This is actually, I don't know, this is supposed to be a video, but it doesn't seem to run. It's a launch, but you've all seen launches. I apologize for that, but here we are on our way. What? Okay. Oh, there we go. And there should be sound as well, because it's even better. Well, I have to tell you, it's a lot louder when you're actually there. But nevertheless, we're on our way, and it only takes 8.5 minutes, of course, to get into orbit. And then we spend the next roughly day and a half doing a rendezvous with the telescope. But while we were, and that was the job, of course, of the commander and the pilot, those of us who were doing spacewalks, we right away started working to get our spacesuits ready and check all of the equipment and all the tools and everything we were going to need. We pack all of the critical equipment in these foam boxes so that they are protected from the launch vibration. Tools, absolutely incredibly important. We had about 200 tools on board. We were planning to use maybe 50, 75 of them, and then we had a lot just in case something went wrong. And we had to tie them all together so we could take them outside. Getting the spacesuit ready, we take a whole evening to work on this and check them out. Remember, a spacesuit is like a miniature spacecraft. It has to provide you with oxygen, with pressurization, with thermal control, and so on. Your life depends on your spacesuit. And you don't want to go outside until you're absolutely sure that your spacesuit is in good working order. putting in extra batteries, carbon dioxide scrubber. It happened to be, this was actually, my wife's birthday is the 2nd of December. My second space flight, excuse me, my wife's birthday is how can I forget that? My wife's birthday is the 5th of December. We launched on the 2nd of December. This was my 4th space flight. It turns out that my second space flight, which had been 3 years earlier, we also launched on the 2nd of December. And so this was the second time I had missed my wife's birthday. So we had to do something anyway. So they brought her into mission control, and the crew, we all sang happy birthday to her. You can't forget the people back home even though you're up in space. But let's get to work. So when it's time to do a spacewalk, I get up early in the morning. I eat as big a breakfast as I can because I know I'm not going to get anything to eat for the next 8 hours or so. Hubble was up at 600 kilometers, which is as high as the shuttle could go. We want it to be above as much of the atmosphere as possible so as not to interfere with the pointing. But that meant that we were getting pretty close to the inner Van Allen radiation belt. So it was estimated that we were going to get about 10 times more radiation than a typical shuttle crew. Nothing to worry about. Made my hair fall out, but never mind. Just a joke. But they put on those radiation monitors just so they could check, and we also put on heart monitors so they can monitor our heart rate. Anyway, I don't normally show pictures of myself in underwear in public, but it's all part of the game, and so it can get pretty cold when you're in the shadow of the Earth. And so the first thing we put on is long underwear, just like when you're going skiing or something. Also, you see that little yellow thing is called a UCD, or a urine collection device. I don't need to say anymore. Most people these days use diapers, but I was traditional. Then over the long underwear, because actually when you're in the sunlight, it can get very hot. And so we have a liquid cooling garment where you can run cold water through tubes that run up and down inside that. So you have one set of underwear to keep you warm and another set to keep you cool. Then you get into the spacesuit itself. First you get into the legs, and then we go in the, I love these pictures because I had hair back then and it was actually brown. Then you have to squeeze yourself into the spacesuit. When you finally get through, it's a nice feeling. And then you put on the helmet. You have a lot of nitrogen in your blood. Anybody who does scuba diving knows that if you go to a lower pressure after you've been down for a while, if you don't do it properly, you can get the bends, the nitrogen bubbles up. Well, we run our spacesuits at about 0.3 of an atmosphere. The more pressure in a spacesuit, the more rigid it becomes, and we want to be able to move around. So we fill the spacesuit with pure oxygen. We don't want to waste any of the pressure on nitrogen. You don't, for a short period of time, breathing pure oxygen is okay. But if we go from, a higher atmospheric pressure down to 0.3 of an atmosphere, we run the risk of getting the bends. So after we get in the spacesuit, we actually have to breathe pure oxygen for about 40 minutes, 40 minutes, to get enough of the nitrogen out of our blood so that we're not going to get decompression sickness. And now we have a little movie of what we actually did, and I'll narrate it for you. We should turn the sound down so that I can talk. So this is just a cartoon of of Hubble. Some of what you see in this, you've already seen slides of, but it was a nighttime launch. We launched at about 4 o'clock in the morning. When you're going to do a rendezvous with something, you have to do it right after that object passes over you, and it just happened on December the 2nd. That happened to be 4 o'clock in the morning. A lot of my friends complain, why couldn't you have launched in the afternoon at a more reasonable time of day? But, this is celestial mechanics. So in any case, we're doing the rendezvous at this point, And it was really exciting. You know, when you first see the telescope, it's just a little point of light, and then it gets closer and closer and bigger. Then we reach out with the robotic arm, grab the telescope. We're getting all of our spacesuits ready. And I talked about putting on the radiation monitors. That's a heart monitor as well. Getting into the spacesuits, and then that magic moment when we actually open the hatch, and there I am coming out on the first day of the 5 spacewalks, ready to hopefully fix Hubble. In every spacewalk, one of us, in this case I was actually attached to the end of the robotic arm, and my colleague Story was floating free. Now both of us are attached to the shuttle with a safety tether. The first job we had was to replace the gyroscope, so you can see me there undoing the bolts. Story is actually inside, and he would then take out the gyroscope package, hand it to me, I'd hand him the new one, he'd put it in place, and I'd put the bolts back in. And everything worked fine replacing the gyroscopes, and we thought, oh, this is great, you know, our first big job, and it's gone beautifully, until I went to close the doors. And well, there we are, that's the actual one of the gyroscope packages, and we put them in thermally controlled boxes. That's what we brought the new ones up in, and then we put the old ones back where we'll take them back home. The door would not close properly. This would have been a disaster, and I don't have time to go into the details, but it took us about an hour to figure out what was the problem and come up with a solution where we had to make an unusual use of a special tool that we had on board. And we finally, it took 2 of us, and we were finally able to get the door closed. Of course, after that, they understood what the problem was. Now, the problem with the solar, that is the solar array which you see here, and it rolls up like an old-fashioned window shade. And that folded up, and we brought it home. The other solar array had a problem. You can see those little stiffening rods here. It was buckled, some sort of thermal stress. So the second day of spacewalking, which the plan was to bring both of those solar arrays back home, but the one that couldn't fold up, we knew we couldn't bring it back home, and so we changed our plans, and so the idea was, Kathy, we released the solar array, and Kathy just took it and we put it out in space. And of course, it doesn't have any rocket propulsion on its own, so we had to fire our maneuvering rockets, and you'll see what happens when the exhaust from our maneuvering rockets hits the solar arrays. You have to be very careful when the shuttle would go up to get near Hubble. We don't want to do that to the real solar arrays, and we don't want to do that to the International Space Station. But anyway, that allowed us to install the 2 new solar arrays. The old ones were having a problem because they vibrated too much, and so the European Space Agency, which provided these, built a new arrays, and we installed them. Now, this is the 3rd day of spacewalking. Once again, I'm on the arm, and here we are. This is what you saw me practicing underwater. And it's a really good feeling when you're up there doing the real thing, to have the feeling, I've done this before. I actually know what I'm doing. I feel comfortable. And sure enough, it all worked. We took out the old instrument. This is the new one. This is the little mirror which picks off the light, was protected. We had to remove the protection. And we had anticipated all sorts of problems. We had plenty of tools. We had hacksaws and hammers. We were ready to do anything, but it just, everything worked beautifully. It went in perfectly, and as I said, it's taken a lot of great pictures. That's the old one which we removed, which we put back into the container, brought back home, and for a while it was actually on display at the Smithsonian.
Let's go back to point. There we go.
You can see by standing on the arm, it's very convenient because I can hold on to big things and move them around. much easier than if I were trying to hold on to it with one hand and move myself around with the other hand. So here we are now on the 4th day of spacewalking, and now the rest of the optical corrections. We put in one instrument with optical corrections built in. This had all the other of those little mirrors. That little instrument I showed you, which is in the Smithsonian, is actually inside here, underneath that cover. Now Kathy is holding on to it. She can't see where she's going. It's a very tight fit, so Tom is actually inside the telescope to guide it in along that track. And we have to, finally, when we get it in, we have to position it to 1 or 2 millimeters, and then there's special clamps which will make sure that it's in absolutely the right position. They got that installed, and then, as I said, there were about a dozen other things we had to do. This is how we use our power tools, which it makes things go much, much faster, and it saves a lot of wear and tear on your wrist. Look at all those tools that are hanging on the tool carrier on Kathy's chest. Every one of those tools has to be on a tether, because you don't want your tool to go floating off into space. That's very bad form for an astronaut. After every spacewalk, we have to clean out the spacesuits, disinfect them, dry them out. Nobody's inside that suit, by the way. Astronauts are flexible, but not that flexible. When we were up top changing out the magnetometers, we discovered some peeling paint. This was something that was not planned. We had to make some special covers, and on the 5th and final day of spacewalking, this day I was the free floater and Story was attached to the arm. We had to go all the way up to the top of the telescope again and attach those covers onto the 2 magnetometers, which we had installed 2 new magnetometers because both of the ones that were on there had failed, even though magnetometers are fairly simple. And then it turned out that the motor to deploy that solar panel didn't work properly, so we had to deploy it manually. But it extended, you can see there's now some special insulation over those stiffening rods. And there I am. They wanted us to stay outside until everything was done and proper. But here we are coming inside after the 5th and final spacewalk, and despite the fact that a lot of people thought that this mission we were trying to do too much, but it all worked. We did it. And so all that remained now was to put Hubble back into orbit, and that's the brand new Hubble Space Telescope as it was in December of 1993. Of course, since then, another mission took off those solar panels and put on even newer ones. But there, Claude releases the telescope from the robotic arm, and now we have to use a special technique to move away from it without pluming it with our rocket exhaust, but that's what the pilots get paid all their big bucks for. And there we are. It looks like Hubble is moving away from us. Of course, we're actually moving away. That's an IMAX camera that Kathy's using there, and we have radar rangefinders taking lots of pictures to document what we were doing. And that was our last view of Hubble. I have to say that I started life as an astronomer, as you heard, and both as an astronomer and an astronaut, being able to put my 2 hands on Hubble was certainly the thrill of a lifetime. While we were out there, I was able to take a few pictures just to be able to show people what it's like out working with Hubble. This is right after we had installed the wide field camera. The ground, Houston wanted 5 minutes or so just to check out the electrical connection to make sure that it could turn on, because if something had gone wrong, we would have had to go and try to fix it. And so this is what it looks like when you're out there on the end of the arm, and there's my partner's Story, there's Hubble. Very wide-angle camera, so the picture is a bit distorted. You have to take my word that the Earth is not flat, right? Okay, we went around it every 95 minutes. And every once in a while, even when you're working hard, you know, from inside they would call, hey, sunset in 30 seconds. And I love sunsets from space. sometimes you just have to stop and smell the flowers, so to speak. Well, there's no flowers up there, but it's nice to watch the sunset. This is an astronaut's view looking up at Hubble. It's big. It's about 15 meters from top to bottom. And one of the great thrills was when we were working up at the very top from the magnetometers, 15 meters away from the shuttle. I really felt like I was now in free space. Of course, not a good place if you happen to have vertigo. It's a long way down, but this is one of the memories that I'll never forget, is just floating up there. And of course, we are attached to the end of the arm, but I just wanted to see what it would feel like if I let go. I wasn't going to get lost in space because I was attached, but it wasn't pulling on me. And it was really an extraordinary experience because, when you're holding on, you're part of the shuttle. I could push and pull and I would react my force against the shuttle. I let go, and all of a sudden I was a free-floating satellite, and I really psychologically felt totally different. It was an amazing experience. I wish I could have spent more time doing that, but of course we're out there. NASA doesn't send us up there so we can have existential experiences. They send us up there to do useful work, and that's what the whole thing is about. But in any case, there was the Hubble Space Telescope. As you see, we knew that we had accomplished everything that we set out to do. But what we didn't know, were those corrective optics actually going to work? And the thing is, you can't turn on the instruments right away. There's a little bit of atmosphere that sticks to the outside of them, and you have to wait about 2 weeks for that atmosphere to go off into space, because if you turn on the high voltage too early, it will cause sparks and you lose your electronics. So it wasn't, and again, another moment I'll never forget. It was New Year's Eve now, in between 1993 and 94. It's about 1 o'clock in the morning. We had had a party. I was cleaning up, and the telephone rang. And it was an old astronomer friend of mine who was working at the Hubble Space Telescope Science Institute in Baltimore, Maryland. Happy New Year, Jeff. Hey, Happy New Year. Jeff, do you have any champagne handy? And yeah, we had half a bottle still in the refrigerator. He said, well, why don't you pour yourself a glass? I'm really not supposed to tell you this because they want to make an official announcement to the press once the holiday is over, but we figured somebody from the crew should know that we got the first pictures back and it worked. Now, this was not a suspense story. You all knew that it worked, but you have to appreciate what this meant to us, back then, that, not only had we done this incredible mission to put all the corrective optics in, but my gosh, it actually worked. And of course, the rest is history, because Hubble has gone on to rewrite astronomy books many times over. These iconic images, which, they're in school classrooms all over the world. This is, the birth of stars, let there be light. It's almost biblical. I get shivers sometimes still looking at it. And then the death of stars, they blow off their atmospheres in these planetary nebulas, which look like the creation of some psychedelic artist. But this is the universe we live in. It's just extraordinary, the images that Hubble has brought back. And the other wonderful thing is all of these images are freely available on the internet for anyone, anywhere in the world. I don't have time to talk about all the different scientific discoveries Hubble made, but I needed to say something about the science. So let me talk about what I think, for me at least, is the most significant change in our understanding of the universe that was brought about by the Hubble telescope. First of all, Einstein, in his general theory of relativity, demonstrated that matter can distort space and bend light. And so if you have a galaxy or group of galaxies between you and a faraway object, it can actually act like a lens and focus that light. And in fact, if the matter is symmetrically distributed, you get these beautiful, they call them Einstein rings. And by studying the structure of this ring, you can determine the distribution and the amount of matter inside. And what this allowed astronomers to do was to confirm something that had been suspected even in the middle of the 20th century, that there's about 5 times as much matter in these galaxies as we can see. This is the so-called dark matter that you may have heard of. But that's only the beginning of the story, because one of the most important observing tasks that was set for the scientists using Hubble was to do what Hubble was originally intended for, which was to look at the really far away galaxies, which is where you can actually measure the structure of the universe. Now, Edwin Hubble, after whom the telescope was named back in the early 20th century, he was able to measure both the distance to galaxies and the speed with which they were moving towards us or away from us by measuring the red shift or the blue shift, if you're familiar with that. And what he determined was that, on the average, most galaxies are moving away from us. Moreover, the farther away they are, the faster they're moving. This led to the concept of the expanding universe, where the farthest away galaxies are moving away at a large fraction of the speed of light. Of course, what everybody knew, because everything in the universe has gravity, right? And so just like when you throw a ball up in the air, gravity slows it down. And everybody knew that the expansion of the universe was gradually slowing down because of all the gravity in the universe. But the rate at which it was slowing down was very important, because that would give us information about how much mass and the actual structure of the universe. The dark matter has gravity just like regular matter. It's only that we can't see it. It doesn't interact with electromagnetic radiation. So dark matter and regular matter are all going to slow down the expansion of the universe. And so there were 2 observing groups which were given the tasks independently, because this was so important, determine the rate at which this expansion of the universe is slowing down. And they didn't publish anything for 1 year, almost 2 years. What's going on? Well, finally they got together and compared their results, and the reason they hadn't published was because what they discovered was so unexpected that they thought, we must have made a mistake, because what they found is that the expansion of the universe is not slowing down. It's accelerating. It's getting faster and faster. This has been attributed to a strange thing which we call dark energy. And it's great to give something a name, because it makes it sound like you know what you're talking about. But in fact, we don't have a clue what dark energy is. But the universe expansion is accelerating. There was the Big Bang, and so what we've found by using actually other satellites looking at the remnants of the radiation left over from the Big Bang, this is the cosmic microwave background, and by looking at certain aspects of the clumpiness of that, astronomers and physicists could determine that, in fact, this dark energy, which we don't have no idea what it really is and how it works, but it's almost 3/4 of the universe. And by the way, the dark matter is another almost 1/4 of the universe. So, in fact, 96% of the universe, we don't know what it is. Everything, and I'm sorry for any students here, but everything that you're studying in physics and chemistry and all this good stuff only applies to about 4% of our universe. But, that's what makes science exciting, isn't it? Every time you discover something, new questions arise. And obviously, the attempt to understand and measure dark energy is getting a lot of attention from astronomers now. So something for the future, you know, what the outcome of it all will be. But as I say, this has fundamentally changed our concept of the universe that we live in. And it came, and that's why I think that, for me at least, it's the most important discovery of the Hubble Space Telescope. And I just want to end by reminding you that last Christmas Day, we actually launched the Webb Space Telescope, which has now the Hubble telescope, remember, used the telescope technology of the mid-20th century. Astronomers on the ground at the latter part of the century they wanted to make much bigger mirrors. You can't make it out of a single piece of glass, and so the biggest telescopes on Earth are made of multiple mirrors, which are all joined together. And so that's the telescope technology that Webb uses, these little beryllium mirrors, gold-coated. And of course, the whole thing had to be able to fold up. It's huge. This is a full-size mock-up of the Webb telescope. It's designed to look at objects. Oh, this is the launch on an Ariane rocket. And that's an artist image. And actually, I was watching the NASA broadcast, and you can actually see this is the last view that we had of the Webb telescope when it was released from the rocket and was just floating away. It's not going to be going around the Earth like Hubble is, because it's looking at objects so far away, and because the universe is expanding, the radiation is shifted towards the red part of the spectrum, and actually most of it is shifted into the infrared or heat part of the spectrum. So the Webb telescope, unlike Hubble, which looks at optical and ultraviolet radiation, a little bit of infrared, but mostly optical and ultraviolet, shorter wavelengths, the Webb telescope looks at infrared radiation, which is heat. And if you're going to look at heat, your telescope has to be really cold. I mean, imagine if the Hubble telescope was all lit up with lights inside. You wouldn't be able to see anything. And so the Webb telescope is now in place about 1.5 million kilometers away from the sun on the other side of the Sun-Earth line at the so-called Lagrange point. And it's looking at infrared radiation. So here's a comparison. The actual clarity is similar to what we get from Hubble, but what you're seeing on the left is the universe in optical light, and on the right you see a much different view of galaxies because you're looking at infrared radiation. Now, we've had infrared telescopes before. Before the Webb telescope, the biggest infrared telescope was Spitzer. But remember, I talked about diffraction limit and the size of your mirror. Spitzer was a much smaller telescope, so this is the best, sharpest view that Spitzer could get of certain infrared objects. This is what Webb has been able to do. So it's opened up a new world for us. It's, you know, it's only just started its observing program, and I hope that it produces as much excitement and new concepts of our universe just like Hubble has done. But of course, Hubble is still in good shape, and in fact, I hope it continues to operate for quite a while. As I mentioned before, we were the first servicing mission, but Hubble was serviced 4 more times after that. The last servicing mission was in 2009. They replaced everything they possibly could and left Hubble essentially like a new telescope. And that's really the value of servicing, and with all new instruments. So remember, even if Hubble had not had any optical problems, when it was launched, it was a telescope of the 1970s technology of instrumentation. Now it's a 21st century telescope with almost 1,000 times more sensitivity than it would have had when it was first launched. That's the real value of servicing. So at the moment it's in great shape, and certainly for me, as I said, both as an astronomer and an astronaut, having been able to be a part of this great adventure has been a thrill of a lifetime. I'm incredibly thankful that I've been able to do it, and I hope you can see, I mean, I don't know how many times I've talked about Hubble, but I never get tired of it, because every time I tell the story, it's sort of like being back there all over again, and I get excited. But that's the story of what we did, and looking ahead a little bit into the future. And at this point, I'd be delighted to answer any questions you may have, and thanks for your attention. I guess we're going to sit down?
Yes.
Okay.
We sit in the middle,
Okay.
and we sit. Yeah.
I'll pull yours.
Okay.
So we will now take questions from the public. I can help if someone wants to do the questions in Portuguese. I can translate. We are also receiving questions online.
I am bad speaking in English, okay? But
You can ask in Portuguese and I translate.
Quanto mais longe estiver o objeto, portanto, mais a lente tem que ficar lisa e sem defeitos. Só que depois nós temos que fixar o objeto. E como é que isso se consegue com um telescópio que vai variando a sua inclinação, sabendo que ele está dentro de um ponto de Lagrange, que é altamente portanto,
Okay, I think
não,
I've got. So
okay.
your question is that the farthest the object that we want to observe is, the flattest the mirror has to be, and how can we then afterwards focus? And I think that he thinks that the telescope is in a Lagrange point.
The Webb telescope is in a Lagrange point. The Hubble is going around the Earth.
Yeah.
I'm not sure about the question about focusing. I
About
mean,
focusing.
everything that the telescope looks at is so far away that once the telescope is focused, it's not like binoculars where you have to keep changing the focus when you're looking at things that are near you and far away. I mean, even looking at planets in our solar system, they're so far away that effectively they are at infinity, and so you don't have to continually change the focus.
Portanto, mas passamos depois a outra pergunta, depois falamos. Portanto, o telescópio não está no ponto de Lagrange, está numa órbita, o Hubble está numa órbita à volta da Terra. Exato.
O objeto vai sempre alterando em termos de
Desculpa, é focar para infinito.
sim,
Na prática está
não é
tudo
só,
no infinito.
não é só focar, é como é que ele consegue acertar a órbita de modo a estar sempre a focar o objeto.
So his question is how he can, the attitude of the telescope in order to be able to point
Yes.
to the same place.
Because the telescope sees so sharply, you have to be able to point it very precisely, as you ask. The pointing of Hubble is done by what we call control moment gyroscopes. Hubble has no chemical thrusters, no rocket engines on it. You have constantly spinning gyroscopes in 3 different directions, and by varying the speed of those gyroscopes, by conservation of momentum, you get the telescope to move and point wherever you want it to go. That's how it works.
Okay, thank you.
Quantas vezes é que o telescópio Hubble amplia a imagem para vermos?
How much does the telescope amplify the image?
You can't really talk about magnification in that sense that we do with a pair of binoculars, because, I mean, you see pictures of those galaxies. Well, I mean, each of those galaxies is, 100,000 light years across, or even bigger. So, talking about the actual magnification of a telescope like Hubble really doesn't make so much sense. I don't know what the actual number would be. If you have a small telescope and you're looking at things nearby, then yeah, you can talk about the magnification. But with Hubble, the important thing is how much light it can gather, because you're looking at objects that are very far away, so we don't get very much light from them. And so that's why the bigger your mirror is, first of all, you get a sharper image because you have less diffraction, and you collect more light, so you can see objects that are fainter. And so that's really the important thing when you're dealing with a telescope.
Precisas de tradução?
No, thank you.
Temos aqui mais
Can I? Okay, thank you very much for doing what you did.
Speak into the mic.
Okay, thank you very much for doing what you did and sharing it with us today. It was an honor to be here to hear you. About the Hubble telescope, you said it was serviced 5 times. I know there is no more space shuttle, but is there any plan on doing it again using some other?
No, we just have to hope that it keeps working. The space shuttle was a remarkable vehicle, and it was an extraordinary platform for doing spacewalks, and really was what allowed us to not just take Hubble into orbit, which could have been done by other rockets, but as a platform for doing the spacewalks with the robotic arm and all of the equipment that we could take. We don't have another spacecraft which is able to do that. People have thought about, could we modify a spacecraft and make another EVA, spacewalking platform? I think it's unlikely. I mean, Hubble is getting old. Someday it's going to fail. I don't want to say that the Webb telescope is a replacement for Hubble, because it really is not. It's an infrared telescope, and if Hubble does fail someday, we will really miss it. There are plans that NASA is thinking about for building a much larger optical telescope to put into space, but when that would actually happen, I don't know. So we just have to hope that Hubble keeps working. They take very good care of it. But everything has a finite lifetime, and we just hope that Hubble's not near the end of its lifetime yet.
So I think we are all familiar with the way stars are presented in the Hubble telescope, the familiar four-pointed stars, and how James Webb has, instead of 4, it has 6. Why does Spitzer only show balls as the stars instead of having points?
If you're talking about the points that seem to come out of the stars, those are caused. Remember, I explained how the telescope works. The light comes down, bounces off the main mirror, comes up, bounces off the secondary mirror. Well, you need something to hold that secondary mirror in position. And in the case of Hubble, it's those bars which cause those rays to come out in the images. With the Webb telescope, it gets a little more complicated, and as you said, it has 6 rays coming out. But if you looked, remember, the Webb telescope is made up of a lot of smaller mirrors, each of which is a hexagon, and that's why you get the 6-sided diffraction patterns. So every telescope is a little different depending on whether it's a multiple mirror telescope, and also what support structure you have for the secondary mirror.
But my question was, why doesn't Spitzer show those bars? Is it because it doesn't have enough accuracy?
The image from Spitzer doesn't show this 6.
Oh, well, the image from Spitzer, it's because if you notice, the image from Spitzer was much fuzzier. You're only going to get those diffraction rays if you are nearing diffraction limited, and that's why you don't get them from Spitzer. Sorry, I didn't understand the question quite at the beginning.
Há milhões de anos, as baleias eram mamíferos, viviam em terra. E ameaçadas e como seres inteligentes, adaptaram-se ao mar. Nós, possivelmente, teríamos o mesmo caminho, se formos suficientemente inteligentes. Isto é, depois de olharmos para as estrelas quando éramos pequeninos, e não desenvolvemos assim tantas nossas capacidades humanas, do meu ponto de vista, mas desenvolvemos imensa tecnologia. De que maneira é que essa extraordinária viagem para o espaço será a ferramenta que nos poderá fazer olhar para o fundo do mar? E de que maneira é que, por reflexão, poderemos salvar o ser humano, nomeadamente? Obrigada.
Desculpe, não entendi o início.
As baleias eram mamíferos que foram suficientemente inteligentes como seres vivos para se adaptarem ao mar, ao oceano. Elas viviam só em terra e passaram a viver no mar e adaptaram-se. E sobreviveram, não é?
Sim.
De que maneira é que nós, seres humanos, não teríamos o mesmo destino? Isto é, para nos salvarmos perante as alterações climáticas e não só. Portanto, a alteração do planeta, será que o nosso destino também não vai ser o fundo do oceano? E de que maneira é que essa extraordinária viagem...
Desculpa, acho que isso não é uma pergunta para o Jeff Hoffman.
Acho que sim. Acho que só um ser extraordinário como ele, com a experiência que teve e com essa percepção de querer, é que poderá talvez responder.
Okay, I will translate.
Sure.
She is talking about the whales that were initially terrestrial animals and they adapted in the sea to survive.
Okay.
And if you think that humans will try to adapt themselves to the sea, or I would say to the space. Or to space.
That's actually
to
a
run
very
away from climate change.
It's an interesting question because human beings, we evolved here on Earth with an atmosphere, with gravity. Whether or not humans will be able to evolve and physically adapt to the conditions of space, that's almost a question of science fiction. Genetic engineering, changing the human genome. What we're trying to do now is, given the genome that we have and the types of human physiology that we have, is to figure out what we can do to be able to adapt, not so much to evolve in terms of evolving like land animals did when they went back to the ocean and became whales and dolphins, but to learn how to keep the human body healthy without gravity, with extra radiation and all the other parts of the space environment which normally we don't deal with. That's the challenge of space medicine, is figuring out how to keep humans healthy in the space environment. And we've learned a lot about the effects of zero gravity on the human body without any special, what we call countermeasures. When you are exposed to zero gravity for a long period of time, your bones start to lose calcium, your body loses liquid, your heart changes its shape, it doesn't have to work as hard. None of which is going to bother you as long as you stay in space, but when you come back to the Earth, then it becomes a real problem. And so that's why when we have astronauts now spending 6 months or more up on the International Space Station, they have to spend 2 to 3 hours every day exercising to keep their muscles in shape, to put stress on their bones so that their bones don't lose calcium, and so on. So that's really the challenge that we work with now. Perhaps someday the human species will evolve so that we can naturally live in environments with different levels of gravity if we someday go to Mars, which has a gravity of about 1/3 of the Earth. But that's for the far future, and as I say, for now, that's science fiction. Right now, we're working to learn how to keep humans like us healthy in space.
Hi. I wanted to make a question about how in the James Webb Telescope the mirrors are hexagons, right? And there's little nooks in between the mirrors. And how doesn't that affect the light in some way?
I'm not sure I understand the question. Did you?
I can try to phrase it
James
better.
Webb Telescope,
Yeah.
how the mirrors work.
Well, I mean, how the mirrors work on the Webb telescope, we learned how to make telescopes composed of many mirrors. They're called multi-mirror telescopes. We learned how to do this here on Earth. It's rather complicated because each of those mirrors is like a separate telescope. And what you have to do, and the way the Webb telescope is organized, behind each of those mirrors, there are 7 pistons which you can use to push or pull. So what they have been doing, Webb was put into space over 6 months ago. And during those 6 months, they've been adjusting all of those mirrors to make sure that they're all focusing at exactly the same point and that the curvature of each of those mirrors are right. And that's basically what you have to do when you have a telescope made of many mirrors. You have to adjust each mirror so that they all work together, and then when you've done that, it acts like you have one big mirror, and that's what's been done with the Webb telescope.
Mais uma pergunta aqui.
Thank you very much for your presentation and brilliant insight of what being in space may be like. And on that, I would like to ask you to share with us how those experiences changed you as a man, as an astronomer, as your vision of Earth, of our planet.
It's always a hard question when people ask you, how does this experience change you? I tell them you really need to ask my wife. She's probably in a better position to tell you. But certainly, I've been very privileged to have been able to look at our planet from a very different perspective than most people are able to do it. It's a perspective that I wish could be shared with everybody in the world, because what we need to understand in order to preserve our planet, we have a lot of problems, and many people are unable to understand that we are living on a finite planet. The Earth is a finite system. You can't do anything we want to our planet and expect that it's not going to have any impact, whether it's to our oceans or our atmosphere. You saw the first picture that I showed of the Earth's atmosphere, how thin it is. That's one of the things that every astronaut who goes into space will comment on when they come back. You look back at the Earth, you go outside on a beautiful day like today and it looks like the blue sky goes on forever. And many people, the way they treat our atmosphere, they seem to believe that you can put anything we want to into the atmosphere and it's not going to make any difference. Well, that's not true. Our atmosphere is a very, very thin layer and that's all that's protecting us from space, which is totally hostile to life. That sense of the Earth as a finite planet is what has to be shared, and the more people who can understand that, maybe then we will have the political will to protect our planet the way it needs to be done. So it's a very important question that you ask, and the perspective that we get from space of the Earth as a planet is something that I try to share whenever possible.
Ok, mais uma questão aqui.
I have here a question in the chat. They ask if dark matter is really, it's called dark because it is dark, or because we don't have a clue on what it is.
No, when we call it dark, because all the matter that we normally know about interacts with light, with electromagnetic radiation. It absorbs light, it emits light, black body radiation. At different temperatures, it gives off different kinds of light. Dark matter does not, as far as we can tell, does not seem to interact with electromagnetic radiation. Why? We don't know, because we don't know what it is. Is it some strange type of particles that we don't know? And, people have been looking with particle detectors up on the International Space Station to see if we have any particles that we don't understand that may be particles of dark matter, but no, we just don't know.
So we could say that it's dark on both senses.
Yeah, it's dark because it doesn't give off any light, and it's dark because we don't know what it is.
Yeah, so more questions?
Posso pôr aqui uma pergunta da plateia?
So you said that the universe is expanding. So are our galaxy also moving away from the center, or we just moving around the center?
Well, you only can observe the expansion of the universe when you are looking at things that are really, really far away, because as I said, when Hubble first discovered the expansion of the universe, the farther away you get, the faster things are moving. When we look at something like, the planets of our solar system, or even the stars in our galaxy, or even the galaxies that are very near us, we don't really see this expansion because things are too close. It's only when things are really, really far away that we can measure the expansion of the universe. So if you're worried about your body expanding and getting too fat, don't worry about it. That's the problem with your food, not with the expansion of your universe.
Eu vejo aqui mais duas questões. A primeira vou passar já aqui.
Please do the two at the same time, because we will soon have to end.
Okay, primeiro aqui esta.
And preferably below 18 years for younger than 18. So, okay, I think that's right. In that case, it's right.
The question about dark matter rose a thought in my mind. If dark matter doesn't interact with light, how would you confirm the correlation between mass and energy that Einstein formulated?
Very good question. I mean, how do we even know that it's there? What we can measure about dark matter, although it does not interact with electromagnetic radiation, it does have gravity. And that's why, when you measure the amount of light that's bending, and you can also study the dynamics of the motion of stars inside galaxies, we can measure how much mass there is in a galaxy by looking at the motion of the stars. And that's how astronomers first came to believe that there somehow was more mass in galaxies than we could see. What Hubble has done is we've been able to make that measurement much more precisely. It has gravitational mass. That's about all we can say about it, because we don't know what it is. But we can measure its gravity, so we know where it is. There are, halos of dark matter surrounding all galaxies. And in fact, it may well be that in the early phases of the universe, when galaxies and stars were first forming, that dark matter played a very important role in bringing together the kind of matter that we're made of. But right now, that's kind of speculation. We really don't know because there's so little we know about dark matter. As I say, we know where it is, we know how much of it there is, we just don't know what it is.
So maybe one last question.
Yes, thank you for your talk. So my question relates to something that you mentioned at the beginning of the talk, which is your current project relating to the production of oxygen from extraterrestrial material. So I wanted to ask you, what kind of material are we talking about, and what is your intention with
Sure, I'll be happy to talk just a little bit. The experiment is called MOXIE, which is the Mars Oxygen ISRU experiment, and ISRU stands for In Situ Resource Utilization, which is a fancy way of saying learning how to live off the land, to use local resources. We need oxygen. If people are going to go to Mars, presumably they want to come back from Mars. I hope a lot of you have seen the movie about the Martian with, Matt Damon got stuck on Mars. He finally made his way, and he got in that big rocket and finally made his way off the planet. That rocket needed a lot of fuel. That rocket needed about 30 tons of oxygen as well as fuel as propellant. Now, you could bring all the oxygen from the Earth and bring it to Mars. We have to bring lots of things from the Earth. I mean, anything that we manufacture, computers, spacesuits, rockets, whatever, we can't manufacture things like that on Mars, at least not now. But to get 1 ton of anything from the Earth to Mars, you have to put a lot of stuff into orbit around the Earth. You need to put rocket engines, and you need a lot of propellant. So it takes we have to launch about 15 tons of stuff into Earth orbit if we want to put 1 ton on the surface of Mars. So to put 30 tons of oxygen on the surface of Mars, we'd have to launch 450 tons into Earth orbit. That's, just for comparison, the big Saturn V rocket, which we used to go to the moon, that could put about 125 tons into Earth orbit. So you're talking 3 to 4 Saturn V rockets, and those are expensive rockets. So, as I say, some things we have to build on Earth and take to Mars, but dumb old oxygen, I mean, if we could get that oxygen on Mars, we've saved ourselves a tremendous amount of expense. And it turns out that we can do that because Mars has an atmosphere. It's very thin, it's only about 1% the density of the Earth's atmosphere, but it's 95% carbon dioxide, which is CO2, O2, oxygen. And so what MOXIE does, just like all of you in high school chemistry have electrolyzed water. You take a beaker of water, you put 2 electrodes in it, you hook it up to a battery, and you split the H2O into hydrogen and oxygen. Well, it turns out you can electrolyze carbon dioxide as well, and that's exactly what we do with MOXIE. We use a solid oxide electrolyzer, and I won't go into the details, but we basically split the oxygen off from the carbon dioxide, and it's just a demonstration. We're only making about 6 grams per hour, which is enough to keep a small dog alive, but it's certainly not enough to launch a rocket off the surface of Mars. But it's the first demonstration ever in history of using the resources from the surface of another planet. And it has worked beautifully. We've operated now 10 times, and it has shown that this process works. And so someday, when it's time to go to Mars, maybe we will actually be able to use a scaled-up version of MOXIE to make the oxygen that it takes to get the rocket off the surface. So that's what our experiment is doing. Thank you for asking. I love talking about MOXIE just like I talk about Hubble, and this was a nice opportunity. And thank all of you who have asked questions. It's been very good questions, and I'm happy I'm able to answer. We could probably spend the whole night here, but I think
Yes,
that's not
but
an
we
option.
can't.
So
Maybe just to close this session, Jeff, you have flown in one of the most brilliant pieces of engineering that men have built, which is the space shuttle. And probably you are one of the few human beings that have been free floating furthest away from the Earth since the time we went to the moon. So for those, for the young people around here and those that are also watching from home, until and during their lifetime, where do you think their dreams can be? How further can they dream?
Well, dreams can take you anywhere you want to, but of course it takes a lot of science and engineering to turn those dreams into reality. You talked about going to the moon. I hope that we are now in the process of getting ready to go to the moon again. It's been a long time, over 50 years, much too long. But the moon is the first step in leaving the Earth. The dream after going to the moon is that we will someday be able to go to Mars and explore Mars. I could talk all night about why Mars is important, but it's a fascinating laboratory for understanding how planets developed, and maybe even did life ever develop on Mars. That's really what the Perseverance rover, which is carrying our MOXIE experiment around, its fundamental purpose is to see if we can find any signs that there was once life on Mars, looking for fossils. And in order to do that, it's actually bringing back samples. It's now preparing samples which in another decade will send another mission to pick up those samples and bring them back to Earth. You can dream much farther away than that because the human mind doesn't have the limits that the human body does and that human engineering does. So I encourage all young people. I mean, how did we get to the moon in the first place? Because there were visionaries who thought that it could be done, and then we had a lot of clever scientists and engineers who figured out how it could be done. So the first step is imagine that you can do something that hasn't been done before. And then, of course, you've got to do the hard work and figure out how to do it. But, that's what makes human progress. And I hope that that continues because, we've just scratched the surface of exploring our universe. And there's just the fact now that we realize that 95% of the universe, we don't even know what it is, that should tell you that there's an awful lot of new science to be discovered, and who knows what it is. But I hope that, maybe in the life of some of the younger people here, we'll figure out what that is, and maybe even figure out how to use it. You never know how these things work out.
Thank you very much, Jeff.
Thank you. I will just translate for the younger here in the room. Vou traduzir só para vocês, porque o Jeff disse uma coisa muito importante para se deixarem guiar pelos vossos sonhos, nunca parem de pensar, porque é a partir de, primeiro é preciso sonhar e depois a seguir trabalhar para a ciência e a engenharia tornarem esses sonhos possíveis. Creio que foi isso também. E também tendo em conta o quanto a gente ainda não sabe, o quanto ainda não sabemos do que é que constitui de facto o universo, portanto, para não se deixarem, para não esmorecerem e pensarem e desenvolverem a ciência que permitirá conhecer cada vez mais. Acho que foi um pouco assim.
Exatamente.
E com isto vamos terminar. We will stop here. Thank you very much for you who have come.
Thank you, Jeff. Thank you very much.
Wonderful.
Thank you.